Welcome student to Radiation Oncology course. I am Dr. Ganesh Kumar Patel and this is lecture number 37 and the title of today's topic is the quality assurance of linear accelerator part 1. In my previous lecture we understood the quality assurance of a telecobalt machine and now we are going to continue with the quality assurance of an advanced equipment in a radiotherapy, that is a linear accelerator. Before we continue, we must understand the quality assurance tests have been categorized in three forms: the mechanical test which includes the couch gantry, collimator and some other test, then dosimetry test, photon beam, electron beam and unflattened beam, and radiation safety test, photon leakage and neutron leakage. Okay, in my previous lecture we didn't explain what is the frequency of quality assurance. The frequency of quality assurance depends upon time factor, because radiotherapy is generally radiotherapy department have a number of patients being treated every day, and depends upon the workload of a patient. It is quite tough to perform all these quality assurance tests like mechanical, dosimetric and radiation safety tests on the same day, but therefore the regulatory body has find a middle way in which they have segregated the quality assurance according to their importance or according to their role in the therapy, and in order to save the time and parallelly keep the safety of a equipment and a patient by performing the required quality assurance for that time. First is the daily quality assurance. These quality assurance includes which can affect significantly the treatment. This is like that it is a quality assurance which is need to be performed daily, so that you can verify the daily performance of your machine, linear accelerator. And another is a weekly quality assurance which includes QA, which needs attention for avoiding errors, uncertainty and treatment process. Because when you keep on using machine, there is a possibility of errors because of any damage, physical damage or electronic damage or any collision, anything that needs to be taken care of by the weekly quality assurance. Then monthly quality assurance includes a stringent quality assurance test which aims to correct all parameters for accurate dose delivery. Then annual quality assurance consists of comprehensive quality assurance tests, aims to include all above tests with additional tests intended to verify manufacturer specifications. So in annual quality assurance, additional tests which are specially designed by the manufacturer before supplying a machine, that needs to be performed also, and that comes under annual QA. So first we understand what is the daily quality assurance in case of a linear accelerator. In linear accelerator, there is no radioactive source and there is no chance of any decay of energy of a beam, and in this case the energies remain monoenergetic, like if it is a 6 MV, 15 MV or 10 MV. But the beam quality, it means that the beam quality, the monoenergetic nature of the beam can be changed because of the electromechanical parts which are being used to produce these energies. So in order to verify, and that is why it is important to verify every day the beam quality, and for this purpose a beam quality check or a TPR 20/10 phantom QA is used to perform daily. So in this text you can see that there is a phantom which is named as a tissue phantom ratio with 20 centimeter depth and a 10 centimeter depth is there. You can see that this depth is 20 centimeter and this depth is 10 centimeter, and chamber is placed such that it should the chamber point of measurement should be 20 centimeter from this surface and 10 centimeter from this surface, and this is why it is called a TPR phantom, 20/10 phantom. Then you required a ionization chamber, Farmer ionization chambers, which is a large volume ionization chamber which is placed over here, And you required a electrometer. In previous QA we have seen that when we were performing a shutter timer error, we were measuring a charge. So with the help with this is to be connected to this electrometer, which measures a charge. Okay, you have to set this phantom on the couch at the ISO center, should be at this point. It should be placed horizontally. You have to move the gantry at 90 degree. Your depth become 10 centimeter, then you move to the gantry at 270 degree, your depth become 20 centimeter. In this way you will collect a charge with the electrometer, and you can verify your beam quality. So as I said that this is a monoenergetic beam, there is a typical values are provided by the manufacturer. So in case of 4 MV, 6 MV, 10 MV, suppose we take an example, the 6 MV should have a beam quality of 0.677 plus minus 3%. So whenever you are performing your TPR 20/10, your value should come within this range. If the value is not within this range, it means that your QA is failed and you need to report your service engineer. Similarly for 10 MV, similarly for 15 MV, and similarly for 18 MV, these are the quality indexes for different energies. Then the second daily QA is the output consistency, because as I said that if your beam quality is hampered or because of any reason, your output can also get hampered. So you need to verify your output. Output, it means that your absolute dose at the value of Dmax, which we will see further, and the value of absolute dose should not deviate from plus minus 2% of the baseline value. This baseline value is being obtained at the time of machine commissioning, which we will understand in further slides. So from that value, the everyday measured value should not deviate more than plus minus 2%. And the third is your laser quality assurance. As I said you that there are generally 3 lasers are being installed in a bunker to accurately locate a virtual point that we call an ISO center. This side a laser is there on this side, and one on sagittal laser coronal, and 2 coronals and 1 sagittal lasers. So these lasers are used for the patient setup, and any error more than 2 mm can cause a setup error of more than 2 mm. So it is mandatory to have the QA of this laser. So you have a choices to perform the laser QA like this ISO aligned device. You can see in the picture, it is rapidly accurately check the laser beam alignment through the ISO center of the machine. It can be used for cobalt, simulator or accelerator, a multi-purpose device used for all these machines. Emphasizes the match between the luminous simulation and radiation field. You can also see your optical field with you can see that at different field sizes it is been marked. But the most easiest way, suppose you have to quickly verify your laser, the most easiest way to use a plain paper. You can see at the picture, suppose your black laser is the laser of left hand sides, and your red intersection is the laser from the right hand side of a machine, left and right hand sides of machine. You can see that there is not a complete overlap. There is not a complete overlap, which you can at a plain paper you can visually see that at the ISO you have to place the paper at the ISO center. If it is not completely overlap, the overlap should be within 2 mm. Within 2 mm. If this overlap is within 2 mm, then it is okay and you can go ahead with your treatment. But if this overlap is not within 2 mm, more than 2 mm, you need to correct this by calling your service engineer. Then the SSD verification, as this quality assurance we seen in the telecobalt machine, but I said you that for SSD verification in LINAC, the difference is that here there are the multiple SSD or multiple rods are given. It means that you not only verify SSD at ISO center, you can verify your SSD at extended SSD also, because in LINAC there are some treatments where their extended SSDs are required. Or you can at even less than 100 centimeter SSD also verify. It means that you can verify your SSD at different distances. In linear accelerator, your source to surface standard source to surface distance is 100 centimeter. Okay, so with the help, you need to just place your device here. It gets fitted, and here it is the rod, and you just the same way you just keep rising your couch. The tip should touch to the couch, and that SSD should see at the surface of a couch. It's the same. So the tolerance is plus minus 2 mm. Then radiation and optical field congruence. In linear accelerator, there is not a single energy like a telecobalt. There are multiple energies like 6, 10, 15. So for multiple energies, you need to perform use a multiple films, because this is a film base and this is a Geochromic film. You can see that the Geochromic film looks like this, and these are the suppose this is a 10 by 10 field size. The same process which you followed in cobalt, build up material you have to place here. Build up should be 1.5 centimeter, because more than 1.5 centimeter if you are using for more energies. You need to expose enough so that you should get enough darkness. You need to mark your field border, and the field border and your optical density should be within 2 mm, which we already seen. Now the most important quality assurance which differs from a telecobalt is the quality assurance of a multi-leaf collimator. We understood in my previous lecture what is the role of multi-leaf collimator in an intensity modulated technique in a 3D CRT and volumetric modulated arc therapy. The quality assurance of a MLC is on prime importance, because this change your whole distribution and this change your outcome. So for this purpose, there are specified quality assurance tests. Like if you will look at this picture, this is a picture of a picket fence test. In a color wash, you can see that this is a picket fence test. This picket fence test, as name suggests, it's like a fencing structure by the picket fence, like a fence structure. In this, what happened? Some pattern of MLC, a pattern which is generally created in a treatment planning system. A pattern of MLC is being planned, and that plan is delivered either on a film or on a portal imager. This is a portal imager. This picture, you can see that this is of a portal imager, and once you deliver this plan, you will get this image, and in this image there are two tests, subdivided tests at static gantry angles and during arc motion. Suppose your machine don't have a VMAT technique and only have a IMRT technique, you need to perform this test at static gantry angles. It means that 0 degree, 90 degree, 180 degree, 270 degree. So at all 4 degrees, you need to run a plan, means exposure beam, and you will find an image on your portal imager, and you need to verify that you can see that any positional error, because this test is specially to check the positional accuracy of a multi-leaf of a leaf, means whether the leaf is exactly taking the plant position, or it is it is going above the plant position, or it is under performing the your plant position. So you can visually verify, or with the software, these dot circles, you can see that with these dot circles, if there is a more red dot circle, that can say that the MLC is not in the planned position. So in this picture, below you can see the table at 4 gantry angles. The MLC position accuracy is 0.23, 0.23, 0.22, 0.24 mm, and the tolerance was 1 mm. The important thing is that the MLC position accuracy tolerance, as you are going with a VMAT technique, the tolerance should be very stringent. So in this case, the tolerance is 1 mm. So this is your MLC first test, that is a picket fence test. Then the picket fence test we have seen for a static gantry angle. Now you know that in VMAT, the gantry keeps on continuously rotating with a variation in the gantry speed. So there is a effect of a gravity, and because of the gravity as well as the internal movement, the possibility of MLC positional reproducibility can affect more as compared to the static gantry angles. So one more test has been designed, that is we call it a picket fence test during rapid arc movement with intentional errors. So in this test, in previous test, there was no intentional error is performed. In this test, a plan is created in a planning system where intentionally some MLCs have been placed out of their other MLC positions. Like here you can see that, here you can see that the spot is more bright. It means that the MLC position is not at the other MLC parallel to the other MLC positions. So an positional error of 0.5 mm is introduced in one pair of leaves, because your MLC forms two banks, each bank have a 40 pairs, 40 leaves here, 40 leaves here, is introduced in one pair of leaves, and a wider gap of 1.5 mm instead of 1 mm is used for another leaf pair. And the purpose of this test is to show that these intentional errors can be detected by visual inspection, like a picket fence pattern, that is sub-millimeter errors in MLC position can be detected by visual inspection. Like I have marked here, you can visually verify these intentional errors of MLCs. Now, the accurate control of dose rate and gantry speed during rapid arc therapy. As we know that during rapid arc there is a change of dose rate with the gantry speed also. That needs also to verify or assure that whether it is performing according to the planned. So in this test, it is to evaluate the ability of the machine to modulate dose rate and gantry speed for accurate dose delivery during gantry rotation. It uses 7 combinations of different dose rates and different gantry speeds to deliver the same dose to 7 strips of a rapid arc plan as shown in the figure below. In addition, an open field of the same overfilled size is delivered for normalization. So in this case, there are some plan is created with 7 strips, which you can see in the picture, and these 7 strips being exposed with the radiation, keeping your rapid arc movement of a gantry with varying doses, 7 varying dose rates. And for normalization purpose, a open field is exposed and both fields gets overlapped, and these results are having the pass tolerance of delta percent. Delta, we call it delta percent variation less than 3%, and average of absolute deviation should be less than 1.5%. So you can see that 1, 2, 3, 4, 5, 6, 7 strips. These are the 7 strips, their positions of MLC at 2 centimeter, 4 cent from here 0 to 2 centimeter, 4 centimeter, 6 centimeter, and this side -2, -4, -6. The delta percent variation means the MLC positions are well within the limit. Absolute deviation is also plus minus 1.5%. You can see at the picture there is no abnormality you can see in this picture. So visually also you can see that your dose rate and your gantry speed is variation. During this variation, MLC has reached to its the planned position. Then accurate control of a leap speed during the rapid arc delivery. As again I want to explain that MLC keeps on continuously moving because it's a dynamic MLC. So because of the dynamic movement of MLC, there is a possibility that because of the speed, MLC will not accurately take the position, because in a complex plan there are very small segments are formed, and sometimes it is possible that the MLC cannot reproduce that position because of the very small segments or complexity of the plan. So that also need to be evaluated in the VMAT technique. So in this test, to evaluate the ability of the machine to modulate the MLC speed and dose rate for accurate dose delivery during the gantry rotation, it uses 4 combination of different dose rates and different MLC speeds. In previous we have seen that 7 dose rates with 7 gantry speeds. In this 4 different dose rates with different MLC speeds to deliver the same dose to 4 strips of a rapid arc plan as shown in the figure, and same open field of the same open field is again exposed to normalize the field. In this also the delta percent is well within the tolerance, and average absolute deviation is also well within the tolerance. So this is your MLC VMAT QA test. Again, now we are speaking about the advanced treatment technique in which there are so many things move simultaneously, and a very large dose is delivered in a shorter duration. It is very important that your isocenter accuracy should be of high stringent tolerance. In Telecobalt we have seen that a 2 plus minus 2 mm was the tolerance, but in case of such advanced technique, the tolerance brought to a plus minus 1 mm, and in this case a dedicated tool is required to perform this quality assurance, and the name of this dedicated tool is the Vincennes-Lutz test tool, because this is first introduced by a scientist Vincennes. So this technique was introduced by Lutz Vincennes, a small metallic ball with a diameter of 2 mm or 2 mm made up of steel or titanium or any tungsten high-Z material, represents the isocenter, and the phantom position is adjusted in 3 dimensions, okay, with a micrometer tool, and a radiographic film mounted perpendicular to the beam, means it should be placed like this is a film, and this test has to be performed at 4 cardinal gantry angles. So this is your a Vincennes test tool, and it has a micrometer tool, means it can change the position with a sub-millimeter values. And here you can see that this is a ball, okay. You have to very small opening, you have to open a very small field size, almost a 2 by 2 field size or 3 by 3 field size, and here you placed a film below this ball, and this ball is placed at the isocenter, and then you need to exposed, or you have to switch on the beam. Once you then you will see these are the dark spots which is formed in a film, which is analyzed in a film software, and you can see that at 4 different gantry angles you can see that the ball position is with sub-millimeter accuracy, 0.04 vertical, horizontal 0.0, 0.15, 0.27, 0.34. So you can see that at gantry 0 couch 45 degree, gantry 0 couch 90 degree, with gantry 90, gantry 0, with different gantry direct gantry angles and with different couch angles. So in this way, this such a stringent isocenter verification has to be performed before taking the patient for SRSRT or VMAT SBRT QoS. Then in short, we will see that for such an advanced technique, the regulatory body has suggested a stringent tolerance limit, which you must see, like SRS, SRT, SBRT, the tolerance limit of your accurate field size for up to 5 centimeter size should be plus minus 1 mm. Accuracy of laser plus minus 1 mm. Shift in center optical field to collimator rotation plus minus 1 mm. Optical and couch plus minus 1 mm. Optical field and gantry axis plus minus 1 mm. Couch lateral, vertical and angular should be plus minus 1 mm, 0.5 degree. This is a mechanical test tolerance limits, and these are the dosimetry test as tolerance test. I said that it is a 1 mm diameter, which highly stringent. Monitor unit response on gantry rotation plus minus 1%, beam flatness constancy plus minus 1%, beam symmetry plus minus 1%, and monitor unit linearity plus minus 2%, and reproducibility of PDD, which we will see in further. So these are the dosimetry QA tolerance limits according to the regulatory body. Now the next important thing is that the output measurements of a photon and electron beam. In case of a telecobalt machine, we understood that how the output being calculated. But what changes in case of a linear accelerator? In case of linear accelerator, the first thing is that there are multiple photon energies where the output needs to be measured, and there are number of electron energies. This is the major difference between telecobalt and a linear. In telecobalt, there was only single energy. In this case, your setup is same. You required a phantom with minimum dimension of 30 into 30 into 30 centimeter cube water phantom, or a simple solid water phantom. Setup is source to water surface distance is 100 centimeter LINAC. Field size is 10 by 10. Chamber should be placed at 10 centimeter depth, and the same chamber, the thimble chamber or a farmer chamber is to be used. In this case, we are not calculating a treatment time. We are going to expose with number of monitor units. So here we start with a 100 MU monitor units has to be fired or has to be exposed the chamber, and your baseline ideal value at the Dmax means your output should be calibrated at Dmax, and that should be 1 centigrade per 1 mu. So it means that if 1 mu is delivered at Dmax, beam should deliver a 1 centigrade of dose. So this is your baseline value, and the protocol which follows is the TRS 398. The formula is the same process, temperature correction factor. Here only there is a no time correction factor. Okay, the same this chamber calibration factor, and in this way you need to find out the output. But when you want to do a output measurement for electron beam, the change is that here the beam is electron, so same ionization chamber, Farmer chamber, cannot be used for the absolute dose measurement of a electron beam. So here the different chamber, which we called a parallel plate chamber, which you can see in the picture, these are different kinds of parallel plate chambers, are used for the purpose of absolute dose measurement. And in this case, because electron beam is delivered with predefined field size, which we called a applicators, and according to the machines, according to the vendor, there are different applicators has been defined, but both the vendor have a common applicator, that is a 10 by 10 field size applicator. There are some 15 by 15, 20 by 20, 25 by 25, 6 by 6, 6 by 10. These are the applicator sizes. There are 6 applicator sizes. Okay, so the electron beam is can be delivered with the help of these applicators only. So you can see in this picture, the applicator is mounted with an accessory to the gantry, below the gantry head. This is applicator. Okay, and here in a water phantom, you have to place a chamber at the depth of Dmax for the output calibration, and output is the same, which is should be 1 centigrade per 1 mu at Dmax, so like same photon beam. The other way to measure the output is the solid water phantom, which I said you that a slab phantom, and this slab phantoms have a inbuilt cavity for inserting a parallel plate chamber or a Farmer chamber, and same way you have to place the chamber at 10 centimeter depth for the absolute dose measurement. Now what changed with the case of electron beam? We have seen that for checking the beam quality index, you required to measure a TPR with the help of TPR 20 by 10. But in case of electron beam, the beam quality is checked by the value of R50. It is the range where the dose reduces to 50% of its max value. Look at the picture. This is the periodic curve for electron beam, and this is the D50 value, and here the RP is the RP, R50, R80, R90. Okay, these are the parameters which are defined for an electron beam, and here you can see that what are Dmax values for different electron energies and R90% values. So you can see that the quality assurance for electron test are same, except the minor changes for the absolute dose measurement as well as for the optical and radial field congruence. In this case, you need to insert applicator for the measurement of optical and radial field congruence. Other mechanical tests are same, and other all mechanical and test which we perform for photon beam are same for in case of electron beam, keeping these small changes. Okay, so we will continue our remaining LINAC quality assurances in our part 2. Thank you.